There is something I do want to bring up from yesterday. So I do want to start there, and that has to do with spherical capacitors. The spherical capacitor equation, when you finish it all up, the capacitance looks like this. It's 4 pi epsilon kappa. I'm going to put that in there. For those people who were here yesterday, I did the whole thing with just epsilon, but I'm going to put epsilon naught and kappa in there and replace epsilon times AB over B minus A. This is based on a spherical capacitor, which again, yesterday I talked about the fact that you can't really make one of these easily, and it's not an ideal way of being efficient, mostly because if you wanted to try and make one of these, you'd have to find a way to charge the inner sphere, and you're kind of out of options. So the way to charge the inner sphere is about drilling a hole in it and then kind of getting a wire out that hole so that it doesn't touch the sides. But then, of course, you now could do it. You could charge it now because you have a wire that accesses the inner sphere. But these are just hard to make, and they're kind of a ridiculous thing to make in general. Yeah.
Doesn't the wire mess up the charges and everything?
Technically, if it's isolated and only touches the inner sphere and allows you to, say, connect a potential difference between, the outer surface and inner surface, it would be okay. It wouldn't be a perfect spherical capacitor because of the hole, but it would allow you to at least charge it up, and then once you've separated the charges, you could just disconnect it. Part of the reason we study this isn't because of that. Part of the reason we study this is because in getting to this equation, there is a way to talk about a spherical capacitor different than this. On the third step of finding the capacitance, you take the electric potential from the inner plate to the outer plate for a point charge. And of course, that's what leads to getting the standard electric potential. But you could go to infinity here and make it a single plate capacitor. Now, in doing that, you get a capacitance for a single plate capacitor, which would be, take all that away, it would just be a sphere. And the capacitance for a single plate capacitor looks like this: 4 pi epsilon naught kappa times, just A. It ends up being the result. What's weird about this is that this is the capacitance of like a planet, because it's a sphere and it has the ability to attract or become charged. So single spheres in space can have a capacitance. Now, this has been used in movies. They make those things that shoot the lightning and stuff. You can use it, and you discharge them. The whole idea of like a Tesla coil is based on being able to discharge up a sphere. Once you have a charged sphere, the amount of energy it can store is going to be related to its capacitance. So one of the things that is interesting is that just a sphere in space can act as a capacitor and can store energy. It sometimes can do so in ways that are not ideal. So understanding that they can store energy is a valuable tool, but I want you guys to keep in mind that a spherical capacitor can be just a single plate, a single sphere on its own. I don't want to spend a lot of time with it, but I do want to at least throw that in front of you. We didn't have enough time yesterday to go through all of it. There are a couple things I want to add to our discussion, and the first one is if capacitance is defined by how much charge is stored per applied voltage, you can also calculate how much energy is stored in a capacitor. We're not going to do the process of proving this, but I want you guys to know that the energy stored in a capacitor is 1/2 CV squared. And we will spend some time proving this, but I want you to kind of get from the beginning that this is the energy storage. And we're going to look at different electronic devices. And part of the things that we're going to see when we study different electronic devices is how they use or consume energy. Capacitors store energy. So we often look at what they do when they store that energy. But when they discharge that energy through other types of electronic devices, those devices consume that energy based on their own properties. Because capacitance can be expressed in multiple ways, there's different ways of calculating the energy as well. I think it should be pretty clear that if you looked at this, you could make some substitutions and find another formula for the energy stored in the capacitor. So you could write it in terms of the charge and the voltage, or you could write it in terms of the capacitance and the charge. Because there's multiple ways to do that, although I present just the one, you should probably come up with the other two. One that has nothing but charge and potential in it, one that has nothing but capacitance and charge in it. I will generally go for 1/2 CV squared, and that's because it's something we're going to talk about today. But please understand, there are two other formulations. So why don't you take 30 seconds and work out what those two other formulations are and have them in your notes. Today we're going to talk about Kirchhoff's laws, and we're going to use this information in our discussion of Kirchhoff's laws. Having these other two will be helpful to you. I don't know how to spell Kirchhoff. I'm going to try and fail. I think it's that.
According to your calendar.
Oh, I spelled it wrong in there. I spell it different every time.
It says there's 2 H's.
2 H's? All right. I just so you guys know, I will never change something once I've written it to correct a spelling mistake, ever. But you might want to. So I will argue that, yes, this is spelled wrong. It's a person's name. And you should know the correct spelling, but two actual other laws. There's first, conservation of energy. That will end up being one of the rules we're going to use. But it's a consequence. The rule that we're going to talk about is about voltage, but it's a consequence of conservation of energy. And the other one is conservation of charge. The other rule is based on conservation of charge. So although we often will say Kirchhoff's laws or Kirchhoff's rules, they're consequences of these two rules. The first one, conservation of energy, is pretty straightforward and is one we're going to use immediately with capacitors. We can't really use this rule yet because for the most part, bless you, we're going to be ignoring one part of circuits for the time being. This one has to do with voltage. And this one has to do with a current, which is the flow of charged particles. We won't really be talking about current for a couple more weeks. But conservation of energy, that's the first of Kirchhoff's laws. And it says that the sum of the voltage drops through any loop in a circuit is 0. So that's the first rule of the first law, that the sum of the voltage drops through any loop in a circuit must be 0. The next rule, again, we're not going to use it, but I'm going to put them both in here, is I don't want to phrase it right. The current into a junction has to equal the current out of a junction. Those are two of Kirchhoff's rules, and these two rules can solve almost any circuit that's presented to you. solving a circuit is you being able to generate a relationship that tells you how the elements of a circuit consume or use energy. That's what solving a circuit means. And I'll say that again, solving a circuit. When I say we're going to solve this circuit, our goal is to figure out how all the elements in that circuit will consume or use energy. So Kirchhoff's laws will do that. And if you're building a circuit, generally your circuit probably has a goal. One of those goals might be to deliver energy to a portion of the circuit. And there's a lot of ways in which that could happen. And it might just be lighting up a light bulb or transmitting a signal or lighting up a screen. Your circuit elements, no matter what they happen to be, they all use energy in a different way. But from the standpoint of the output of energy, there's just voltage and current passing through a circuit, which is why we only need two laws here. All circuit devices are going to use or consume energy through the delivery of charged particles. That's how they operate. Now, to understand a little bit of this, we have to understand a little bit about what constitutes a circuit. And we'll talk right now about simple circuits. None of our circuits are considered complex circuits. They're all going to be considered simple circuits. And although they might appear complex and have many elements in them, simple circuits have some straightforward rules. First, all simple circuits have to be a closed loop, meaning no matter what it is you're doing with your circuit, let's say we have a standard energy source like a battery. If you want to have this battery deliver charge anywhere in your circuit, then both sides of the battery have to be engaged. You can't just use one side of the battery. You've already learned this a little bit because of the electric motors you made. You guys found that there wasn't a complete pathway from the top of the battery to the bottom of the battery, your little thing wouldn't spin. It might not have always made contact, but it had to make contact a little bit at the bottom for energy to flow that caused your thing to spin. So I can't just put a light bulb here and assume the light bulb will light up because it's on the positive side of the battery. When you add a battery to a simple circuit, you are establishing both the zero potential and the high potential of your circuit. And you are providing a complete pathway for those charges to flow. So all circuits have to be a complete pathway from one side of the battery to the other. Now, the very first thing I'm going to do is violate that rule. So, although that sounds great, our circuits that we're studying first are capacitive circuits. So I take a battery, introduce a switch, and I'm going to connect it to a capacitor. And the truth is, I do not have a conducting pathway, right? A conducting pathway requires contact from one side of the battery all the way around to the other. A capacitor, by definition, has a gap in it. The thing is, a capacitor still acts like it's passing current. When we close this switch, the battery is going to apply a potential difference to both sides of our capacitor. That potential difference means that there's going to be motion of charged particles. The negative side of the battery is going to attract positive charges from the capacitor. So positive charges are going to be attracted by the negative side. That will turn the plate that's attached to the negative sign positive. Now, these positive charges will be consumed by the battery and spit out on the top of the battery to then be deposited on the upper plate of the capacitor, making the upper plate of the capacitor positively charged. Although no charges pass from one capacitor plate to the other capacitor plate, charge in the rest of the circuit is shifted so that charges move from one plate to the other. Now, everything I described there is how a capacitor actually works, even though there's not a complete pathway. So because capacitors have this capability of storing charge, they will act like a circuit element that appears to pass charges, even though no charges are passing. So although I said you need to have a completed pathway from one side of the battery to the other, if you're using circuit elements, whether or not they will pass charge, they still act as though a complete pathway is there. Now, this isn't super complicated, but I'll say it anyways. The reason this works is because the electric field between the capacitor plates, right, causes the capacitor to be able to store energy and allows for this motion of charged particles. Now, I do need to handle a couple of details here. When we close this switch, I described the motion of positive charges flowing around in the circuit. That's not actually what happens. But we didn't know that that's not what happened until about 1920. So because of that, all of electronics that had been established up to that point was based on the concept of positive charge flow. So all circuit elements were based on the idea that positive charges were moving through the circuit. But we now know that it's electrons that are moving through the circuit. So with that change, we should reformulate the idea that it's negative charge particles that are actually doing the moving here to see how that actually affects what's happening. So let's play around with that idea that it's not positive charge particles that are moving, but negative charge particles that are moving. If it's negative charge particles that are moving, when I connect the switch and allow the potential difference to be applied to both plates of the capacitor, the positive side attracts negative particles from this plate, correct? Those negative particles enter the battery. The battery, through acid redox reactions, will spit out those negative particles on this side of the battery, which will then eventually allow these negative particles to be deposited on this side of the capacitor. The removal of the negative particles creates a positively charged plate, and the deposit of the negative particles creates a negatively charged plate. The fact that it's negative particles moving through the circuit actually doesn't change the outcome at all. In fact, for years, people attempted to try and figure out an experiment that would show that it was actually positive or negative particles moving through the circuit. And for a long time, no one had come up with an experiment that could successfully do it. In fact, for us, we won't be able to do the experiment that will successfully do this until second semester. We have to learn a little bit more about magnetism to understand how magnetism works for us to do something called the Hall effect, an experiment by Professor Hall, who created an experiment that would determine whether it was positively charged particles or negatively charged particles moving through the circuit. So we'll get there eventually, and we'll do the experiment in class. All right, so simple circuits and Kirchhoff's law. A simple circuit and the application of Kirchhoff's law looks like this. I have a battery, V, and a capacitor, C. Kirchhoff's laws are pretty straightforward. And in this circuit, the second law doesn't matter. The second law only matters if there's a junction in the circuit. Right? There has to be a place where charge come in and maybe go out in two different places. But there's no junction here. There's no fork in the road. Without a junction, the second law doesn't even apply. But the first law says through any closed loop in a circuit, the sum of the voltage drops has to be equal to 0. Now, that's a true statement, but we have to apply some rules to that to understand how to do this. First, a loop is any pathway that goes from one point in the circuit back to that same point. It does not have to include a voltage supply, but it should include circuit elements. So when you're drawing this loop, make sure that you pick a place to start from. I usually start from the voltage supply and try to end at the voltage supply. But there will be conditions in which we can't always do that. So in this particular circuit, I'm starting at the voltage supply. Rule number 1, all circuit elements that aren't batteries are voltage drops and are treated as such, unless you know whether you are going to an increasing potential or a decreasing potential. I know that's a nebulous phrase, and I need to say it again. All circuit elements we treat as having a negative voltage drop, except for batteries. Unless, the unless is important here, unless we know whether we're going to an increasing potential or a decreasing potential. And then you do plus or minus based on whether the potential is increasing or the potential is decreasing. So let me explain how this works, because it's not obvious. In this particular example, if you'll look closely, this is the negative side of the battery, this is the positive side of the battery. I have intentionally drawn the direction of my loop to go from the negative side of the battery to the positive side of the battery. That is an increase in potential. So when I start my Kirchhoff's equation, I'll write positive V representing the potential difference of the battery being added in the circuit. Batteries are active devices. So if you go from the negative terminal to the positive terminal, you are increasing the potential. Now our capacitor, we don't know the state of the capacitor at this moment. We don't know whether the switch has been closed and the capacitor's had a chance to charge up, or whether the switch was open and we're just starting at time zero. One of the things we will be developing is a way of figuring out how long it takes for capacitors to charge in the circuit. If we don't know anything about our circuit element, we assume that it's going to be a negative voltage drop. But we generally know some things about our circuit elements and can help figure out whether we should have a negative voltage drop or a positive voltage drop. For example, we just talked about connecting up this capacitor to this potential difference. If we do so in the way that we have described, we know that this will be the positive plate and this will be the negative plate. When I go across this circuit element, I'm going from the positive plate to the negative plate. That is a voltage drop. So for that case, I will say there's a drop in voltage across the capacitor. I have to put V in there because this has to be a list of voltages. And I'm saying voltage across C for the capacitor. When we have mixed circuit elements, we might have a V with a little C there for capacitor, V with an R there for resistor, inductor, diodes, whatever. Now, once I make it back to where I started, then I have finished the loop, and that's how Kirchhoff's first rule is done. The sum of the voltage drops has to be equal to 0. There it is, we've done what we needed to do. Usually the next step is to go through and replace voltages with how your circuit elements consume or use that voltage. We know for a capacitor that voltage is consumed based on this principle. All right, Q over C, all I did was take our expression for capacitance and solve it for voltage. With that being said, our voltage equation ends up looking like this. Now, I know this is going to sound a little bit ridiculous because isn't this what we have right there? Yes, it is. But appreciate that this is where we're starting. I'm just trying to show you how to use Kirchhoff's relationships. All right? Now, I'm going to have you try this on your own for a minute. See if you can kind of do this. What if I have capacitors in a row? Say one with capacitance 1 and one with capacitance 2, and I apply a voltage to that circuit. What will be the result of doing this? By the way, this is called a series circuit. Anytime we have circuit elements that are in a row, we call that series. Not to be confused with a parallel circuit, which we'll do next. This is a series circuit. So it has capacitors that are in series. I'm assuming you're picking a point in the circuit. You're making a loop in your circuit, and I hope that you are attempting to complete what it is we started here, which was come up with an expression about the circuit. Now, I know this is no big deal, but probably I hope what you have written is something like this. Maybe you've gone the extra mile and written something like this. Now, the battery doesn't know it's connected to it. The battery provides energy to a circuit. It doesn't know that capacitors have been connected. Doesn't know how many capacitors have been connected. Doesn't know if maybe there's other circuit elements involved. The battery merely provides charged particles and maintains a potential difference. From the battery standpoint, the circuit that we have here looks to be just one circuit element out there. It doesn't know that there's two in a row. It might recognize that after a long period of time, it will stop pushing charges into the capacitor because the capacitor will eventually be charged. And therefore, it can hold no more charges. That's the whole definition of a capacitor. It holds a specific amount of charge based on your applied voltage. Once it has that charge, it can't hold anymore. So all the battery sees is some total capacitance. We call this an equivalent circuit. The idea being that we have two capacitors, but the battery charges it as if it sees one capacitor. When we talk about equivalency, what we're talking about doing is finding what the equivalent capacitance is for perhaps a system of capacitors. This is one of the first jobs we're going to have to do with capacitors. In fact, tomorrow you're going to have a pile of capacitors on your desk and a breadboard, and you're going to try and prove something we're going to talk about here in just a minute, that a group of capacitors can be treated as a single capacitor. Our job right now is to figure out how we go from what we have here to some formula that tells us what to do to figure out the equivalent capacitance. Now, we can do this because we have Kirchhoff's laws, and they'll help us. Because our equivalent circuit is going to have to look like all right? That's what our equivalent circuit has to look like. Now, there's something here that I think you guys, maybe through small discussion, could figure out. Can you figure out how Q1 and Q2 might be related? Talk to each other a little bit about what you think might be happening. But I would have you focus on the fact that no charges can be passed to or from this section of the circuit. Right? It's completely isolated because there's a gap in both capacitors. Using that knowledge, can you figure out how Q1 and Q2 might be related? I'll give you guys a minute. A very reasonable expression. So what is being suggested is that Q1 would have to equal Q2. And that's right. In a series, and I'd get this in your notes before you guys walk away. In a series circuit, all of the capacitors in series have to have the same charge. Now, knowing that information, I would like you guys tonight to prove with what's just sitting here that 1 over CT has to equal 1 over C1 plus 1 over C2. I want you to prove that. You should be able to with what's sitting here. In fact, you should prove it for maybe 3 in a row and see if you get the same thing. Try it. It's not hard.